Yeah, thank you very much. Thank you very much for inviting me on this great conference. Very honored. So I want to talk about some finitely presented groups associated with finitely presented dynamical systems. So there are these two notions of being finitely presented as a group or as dynamical systems, which are kind of not really related with each other. It's more superficial. It seems to be, at the first glance, a superficial analogy, but still, in this case, the analogy becomes deep. I will not define what a finitely presented dynamical system is, but in particular, expanding covering maps are finitely presented. So what is an expanding covering map? So let M be a compact metric space, and F a covering map, of course, necessarily of finite degree. Oops. I see. I need to pause before pressing button. We say that F is expanding if there exists some epsilon such and a positive number epsilon and L greater than 1 such that if you have 2 points on distance less than epsilon, then the map expands the distance between them at least by a factor of L. So you cannot have an honestly expanding map because the space is compact, but I just require that it is expanding locally. Come on. So for example, the easiest perhaps example is just angle doubling map. You take the circle R mod Z and multiply everything by 2. It's a double covering map, and it expands all the small distances exactly by a factor of 2. In general, say if you take, for instance, z squared minus 1 as a complex polynomial, then it is expanding on its Julia set. Well, in this case, you can take it as a definition of the Julia set. There will be some compact set on which it is expanding. And that compact set will be unique. Well, you require that it's totally invariant. So preimage is equal to itself. Then it's unique. More generally, you can take any complex rational function such that every critical point under iterations converges to an attracting cycle. Then this, for example, it eventually belongs to an attracting cycle which necessarily contains then a critical point. So here are examples of such Julia sets. So there are two quadratic polynomials, and this is typically how these Julia sets look like. So I want to stress that in this example, when F is an expanding map on compact set M, M rarely is a manifold. Actually, it is a manifold only in very special examples of so-called infranil manifolds. So for instance, fundamental group must be virtually nilpotent then. In all the other cases, it's a fractal like this. Okay, so well, it follows easily that if you have an expanding map, then there is delta. By the way, I don't require any connectivity conditions on M. But nevertheless, there exists delta such that every set of diameter less than delta is evenly covered, which means that the preimage is decomposed into a disjoint union such that on each piece F is a homeomorphism, and each set has diameter less than epsilon. And then if delta is small enough, this decomposition will be unique without any requirements on connectivity of the space. So you have, even without connectivity, you can talk about components of inverse image. Then a natural thing to do is to consider inverse limit of backward iteration of a sequence like that. And F will induce a homeomorphism on the inverse limit, F hat. So you will be able to make a homeomorphism out of this map. And it's called natural extension. It's a very standard construction in dynamics. And it's a Smale space. If you remember talk of Jan Putnam, he defined Smale spaces. And this is an example of a Smale space. In fact, it's a very special Smale space. There is a natural projection onto M just taking the first coordinate of this inverse limit. And it's a fiber bundle, unlike general Smale space, where you have these rectangles covering with local product structure, which are just patched together in some way. Here you can take rectangles equal to inverse images of subsets of M. So it's a bundle. And if you take a small set U of diameter less than delta, then its preimage in this projective limit is a direct product of this set U with a Cantor set. So the fibers are Cantor sets. And now if you have this fiber product, you can look at the monodromy or holonomy. You travel around, and when you come back, this Cantor set is identified with itself in some non-trivial way. So you can take all these identifications, you get a group. So this group is called the iterated monodromy group. So if two sets intersect, then on these fibers, there is identification of the fibers, because each of these fibers are identified with the fiber above the intersection. So there is a natural identification of the fiber above U1 with fiber above U2. And if you take all possible compositions, so for instance, take some finite cover and take all compositions of all homomorphism like that, you will get a group. And it is, as I said, it is called the iterated monodromy group of this expanding map. But in fact, you can do more. You can throw in the dynamics. So remember, this is a homomorphism, and it's obvious that preimage of U is mapped by it to preimage. No, that's not quite true. No, sorry, that's not quite true. Yeah, okay, it is true this way, but it's not a bijection. So we get, in fact, this map is expanding in the direction of M and contracting in the Cantor set direction. So you will get a map from fiber above U into fiber above F of U. So you will get some contracting maps of the fiber above a point will be mapped to a subset of fiber above the image. So you get such local homomorphisms, and now you can generate an inverse semigroup by all these maps. So take compositions of all these homomorphisms, all these holonomy homomorphisms, these homomorphisms, their inverses, you get some semigroup acting on the Cantor set. And now my groups will be the topological full group of that semigroup. So in other words, the group of all homomorphisms of this Cantor set which are locally equal to elements of this semigroup. So I want to patch together elements of this semigroup so that I get a homomorphism. And that's my group. So it's not clear why it's finitely generated, but it's even finitely presented. And as it follows from Laurent's talk, that it's actually even F infinity.
Just using elements of the semigroup or also inverses?
Also inverses, yes. You cannot get a group otherwise. Yeah, I wrote here somewhere. They're inverses, yes. OK, but this maybe this definition is too abstract. Let me give you another definition which is more hands-on. So let F be as above an expanding covering map. So if we take a base point, and then we get a tree of preimages. So suppose the map is of degree 2, so this point will have 2 preimages, each of them will have 2 preimages, and so on, and you get a rooted tree like this. So actually, the boundary of this tree is precisely this fiber CU which I was talking about. Namely, if you take any set of diameter less than delta containing T, then the fiber above that set will be is naturally identified with the boundary of this tree. So this natural extension is precisely a bundle of boundaries of these trees above the space M. So now let's suppose that M is path connected or locally path connected. So this definition will be less general than the one I gave before, but that's still good enough. So if you have 2 points, T1 and T2, and you take a path, because of local connectivity, you can lift by the covering map. So as you lift, you will get, so you have a path from T1 to T2. You lift this path by F. You get paths connecting vertices of the first level then paths connecting the vertices of the second level of these trees, and so on. And these paths will define an isomorphism between one tree and the other. That's exactly this monodromy homomorphism. So as you're moving in M, the fiber moves along, and that's the way how the two fibers are identified if you are moving along the path gamma. Okay. Now to fix one base point and take the tree of preimages, and let me skip to the picture. Like in Laurent Bartoldi's talk, cut off some finite piece of this tree. So find a maximal finite anti-chain. Basically you cut off some finite part so that you are left with some finite number of roots. And then do it in some other way, but so that you get the same number of roots. So here these two trees is one tree. It's the same tree but drawn twice. So you find one such antichain, the other antichain, choose a bijection, and connect the vertices by paths inside the space M according to that bijection. So we take this root, move it here and using some path in M, this here using some path, and so on. Now we can lift these paths. We get isomorphism between subtrees. So this subtree will be mapped to this subtree will be mapped to this subtree, and so on. So it's not an isomorphism of trees because it's not defined on the parts which we deleted. But for instance, you can say that it is an isomorphism, a commanduration. You ignore finite number of vertices, so it's a commanduration of the tree. But maybe a better way is just to look at the boundary and see that these maps define a homomorphism of the boundary. So in fact, the set of these homomorphisms will be a group, and it will be exactly this group VF which I defined before. So that's exactly how elements of this group look like. Okay, so elements, in other words, elements of the group are represented by such diagrams. You have some finite subtrees of the tree of preimages, bijection between the leaves, and paths connecting the leaves inside M. But such a picture doesn't, it represents a specific element of the group, but one element can be represented by different pictures. Namely, if you're given such a picture, you can do an elementary splitting, so-called. You can replace, like this, you can replace one path by its preimages, by its lifts. So this picture and this picture define the same element, and this picture also defines the same element. And if you have two pictures, they define the same element if and only if you can decompose them. Well, not quite true, but morally. You can decompose them to get the same pictures.
Decompose or refine?
Split, yeah. Refine. Yeah, it's the same. Refining and decomposing just makes pieces smaller. So okay, so so far this tree was an abstract rooted tree, but it can be identified with Kelly graph of a free monoid in the following way. So first of all, for every vertex of the first level, choose a path in M from T to that point, from the root to that vertex of the first level. And as before, this will give you an isomorphism of the rooted tree TT with the rooted tree TZ. So that will give us isomorphism of the whole tree with the subtrees of the first level. And that already gives you self-similarity structure on the tree. The whole tree is identified in some specific way with subtrees of the first level. So let me denote, just to save notation. So Z is a vertex of the first level. I have chosen some paths gamma Z, so I'll just write SZ instead of S gamma Z. And these elements satisfy the Kunz algebra relations, in fact. So here I will use, first of all, I will use inverse semigroup notation. So this star is inverse, just to stress the fact that it's not a bijection. This is a local partial bijection. So that is just the inverse map. And when I'm writing sum, I mean union. So it means that these maps which are added are partial maps with disjoint.
What is a gear?
Sorry? PF is that semigroup. So I probably glossed over it. So all these maps S gamma, if you take all paths gamma, the maps S gamma form a semigroup. So that's the semigroup. So that's the semigroup of all maps S gamma on the boundary. So so they satisfy this relation. So if you apply S and then its inverse, you get identity. So it's really inverse because it's everywhere defined. But if you do it other way around, it's not everywhere. The range is not the whole space. So you will get a projection onto the range. And when you add up all these projections, you get the whole space. So that's the Kunz algebra relation. So here's the picture. There's S1 of these maps, the other map. One map identifies the whole tree with the subtree, and the other map identifies the whole tree with the subtree. So if you apply at first this map and then inverse, you get identity. But if you apply inverse and then this map, you get projection onto this subtree, onto this. So when you add them up, you get identity. OK, so these isomorphisms of the whole tree with the subtrees induce an isomorphism of the whole tree with the Cayley graph of the free monoid. Namely, if you take compositions, so you have a map from the whole tree onto subtree. Now, if you compose them, take two such maps, you will get an isomorphism of the whole tree with a subtree on the second level. If you have three such elements and compose them, you get isomorphism of the whole tree with the subtree of the third level, and so on. So if you take n maps like that, take their composition, will be isomorphisms of the whole tree with a subtree of nth level. So you can encode the root of that subtree by this word. So in this way, you get a bijection between words, between the free monoid and the vertices of the tree. In fact, this product, as I mentioned, I didn't prove, but I mentioned that this set of maps of the form S gamma is actually a semigroup. So if you multiply them, you get it is also S gamma for some path in M, starting at the root and ending in the corresponding vertex. So here's what's happening. So we have these two maps identifying the whole tree with the subtree. When you compose these maps, you are taking lifts of paths. So when you draw lifts of paths, they will look something like this. And black is the tree of preimages. So you get, in fact, two trees. One tree is obtained by lifting the paths, and the other tree is obtained is the tree of preimages. And they don't coincide. They actually, the relation is exactly that one is left Cayley graph of the free monoid, the other one is right Cayley graph of the free monoid. OK, so again, so I will denote by x star the free monoid and the Cayley graph of the free monoid. So V is connected to Vx. It's the right Cayley graph. And then the transformations that I defined will be a creation and an annihilation in the same sense that if you apply Sx to the vertex V, you get vertex xv. And the inverse is just erasing. And this way you see that it must satisfy those Kunz algebra relations. And now if you take two maximal antichains, so you cut off a finite part of the tree in one way and in the other, and if you have a bijection, then this union is an element of Vf. So as a homomorphism, it acts in the following way. So there is some list of finite words, there is another list of finite words, and bijection between them. And the map just looks in the list, finds if you have an infinite word, it looks at the unique prefix of that infinite word, which is in the first list, and replaces it by the image under the bijection. So you just take a prefix and replace it. So this will be an element of the group. And actually, in this way, that's one of definitions of the Higman-Thompson group. So this is actually one of definitions of the Higman-Thompson group, GD1, where D is the degree of the map. So we have a Higman-Thompson group in our group VF. But of course, that's not the whole thing. So let's try to understand what is missing. So suppose you have a path in M with, I'm sloppy a little bit here, so from the point of the tree of preimages represented by V to the point represented by U. So we have identified tree of preimages with X star in the way I described. and we have a path between them. Then remember there are paths which are products of maps Sx along the word V and along the word U. So they correspond to some paths. They are concatenations of those colored paths in the picture that I showed you. Then gamma V and gamma U are paths from the root of the tree to the vertex. And gamma is a path between the vertices. So you can complete them, put them together to get a loop. So gamma inverse U gamma V is a loop, an element of the fundamental group. And we have a relation that S gamma is this product. So that's easy to check. So we see, therefore, every element of VF can be written as such union. You have these SUI, SVI. These are the elements of the free monoid of X star. And then there is fundamental group. So here is the picture. This is S gamma. This is gamma U, gamma V and gamma U. And then this altogether is gamma prime. This the whole loop. So how the elements? So we see that it does. This group is basically Higman-Thompson group together with the fundamental group. So in the sense that what Higman-Thompson group did, it acted on infinite sequences in the following way. It looked at some prefix and changed it to another prefix. What this group does, it looks at some prefix, erases it, then acts by an element of the fundamental group on the tail, and then appends some prefix. So we throw in some action of the fundamental group inside, and it acts on the tails of words and on the prefixes of the word, something like Higman-Thompson group acts. But you need also splitting rules. So as I showed you on the picture, you represented elements of the group by some pictures, paths connecting vertices, and then you want to know how to split these pictures, how to replace one path by several paths. And this is, okay, so here are some examples. I don't have much time to talk about the methods, how we compute it, but it's very actually easy. So for the angle doubling map, what happens? So VF will be generated by a copy of the Higman-Thompson group and a copy of a cyclic group, and it satisfies the following splitting rule. So A, the element, the generator of the fundamental group, it acts on the infinite words in the following way. So remember, S0 and S1 are creation operators. It's the operation of appending 0 or 1 at the beginning of the word. So when you write star, it's opposite operation of erasing. So it erases 0 and replaces it by 1. Or it erases 1, acts then by A, and appends 0. So this is a recursive definition of the element A. So that's a unique way to define the element A. And now the group VF, it acts in the following way. There will be some finite list of words, another finite list of words with bijection with the first list of words. And for every word, there is a power of A associated to it. And now if you have an infinite sequence, you erase some prefix, apply a power of A, and then append some prefix. So that's how elements of VF, in this case, act. So we have also such relations then. This is equivalent to these two relations, that if you append 0 and act by A, it's equivalent to appending 1. If you append 1 and then act by A, it's equivalent to acting by A and then appending 0. That's basically the same relation, but written in a different way. So if you take z squared minus 1, the corresponding VF is generated by the V by the Higman-Thompson group and two elements satisfying these relations. So A, it erases 1, acts by B, and then appends 0, or erases 0 and appends 1. It erases 1, acts by A, appends 1, erases 0, and then puts it back. So does nothing. So that's another way. Okay, so we've seen that the group is is made of Higman-Thompson group and fundamental group. So there is an image of fundamental group inside VF. So you take just the maps defined by the loops. And it's not a faithful copy of the fundamental group. It's just an image of the fundamental group. And it's the iterated monodromy group. And typically, it's infinitely presented and often has rather exotic properties from the point of view of classical group theory. For instance, it may have intermediate growth, maybe a non-elementary amenable. For example, for z square minus 1, that's historically the first example of an amenable group that cannot be constructed from groups of sub-exponential growth. So like in Michael de la Salle's talk, there were described these operations which preserve amenability. And groups of sub-exponential growth in some sense are obviously amenable, but you cannot construct this group from such obviously amenable groups. So it was defined in different terms by Grigorchuk and Zhuk, and then Bartholdi and Virag proved that it is amenable. And Grigorchuk and Zhuk proved that it cannot be constructed from sub-exponentially amenable groups. Another example is iterated monodromy group of z square plus I. Well, in fact, z square plus I doesn't fit in the definition that I gave you because it's not expanding on its Julia set, but it's expanding in respect to some orbital space metric. So the theory can be generalized to that case. Okay, and due to those recursive relations, due to those recursive definitions, by the way, again, we have such relations. So if you have if you have an element of the iterated monodromy group and the letter x, so appending x and then acting by g will be the same as acting by some element h and then appending y. So that's those self-similarity relations. And we will say that y, and if this is true, then we say that y is the image of x, and this element h will be denoted as g restricted to x and called section. In other words, g, that's the splitting rule, that g can be written as union, action of g can be written as a union of such operations, that you erase x, x by h, and then append y. And then do it for all possible initial letters. So that's how it works. The iterated monodromy group will act on the whole tree. Remember, it's defined by a loop at the root. So when you lift, you get an automorphism of the whole tree. It's not a partial map. It's everywhere a defined map on the tree. And so it will move some vertex of the first level to another vertex of the first level. And this section is just describes what happens in the subtree. So in the subtree, this g restricted to x will act. And this is another element of the iterated monodromy group. Here we have the following general definition, which was also given in the talk of Laurent Bartholdi. A group G of automorphism of the tree x star is said to be self-similar if for every letter there is an element of G such that G acts on the words in the way that it changes the first letter to some letter and then acts by H on the tail. And H is an element of G. So that's the same definition of self-similarity, and we have seen that iterated monodromy groups are self-similar. So the definition which I gave of the group can be generalized to all self-similar groups. So if G is a self-similar group, then we define VG as the group of homomorphisms of the boundary of the tree of this form. So that's exactly before. So there is some finite sequence of words, two finite sequences of words, and the sequence of group elements. And this homomorphism, it does the following transformation. It erases VI, acts on the tail by GI, and then appends UI. So if you take trivial group, if this is trivial, you get exactly the definition of the Higman-Thompson group. But now we throw in this similar group inside. So we get such homomorphism, and that's some group. So V of the iterated monodromy group is the original group of F, but it can be done. So for the first time, this group was defined by Klaus Röfer in 2002 for the case of the Grigorchuk group. He showed that for the Grigorchuk group, this group is isomorphic to the abstract commensurizer of G, and that it is finitely presented and simple. Okay, and just to these groups were the subject of the talk of Laurent Bartholdi. Well, in some more general setting, perhaps, because non-faithful self-similar groups were included in a sense, yes. So, and in fact, one can prove that for every self-similar group G, this group has simple commutator subgroup. It may be not simple itself, but at least it has simple commutator subgroup. Okay, I repeat the definition of a contracting group which was given in the Laurent's talk. So if F is expanding, then the iterated monodromy group is contracting in the following sense, that there is a finite set of elements such that every element of the iterated monodromy group can be written as in this way, where these sections are inside the set N. So there exists a level for every element of the group. There exists a level such that the sections at that level are from this finite set. So in other words, if you take any element of the iterated monodromy group, as you look deep enough in the tree, you will see only a finite number of possibilities. You will see only a finite number of pictures starting from some level. And if G is a contracting self-similar group, then this group Vg is finitely presented. And I gave actually a completely, it's not terribly finitely presented. You can just list all defining relations. Then not very few, but still not too many. So in particular, if F is expanding, then this group is finitely presented. But as I recently learned from the talk of Laurent, and that it's the result of him and Ross-Gagan, that this group is actually of type F infinity. So it's not only finitely presented, but it's kind of finitely presented in all dimensions. Morally, this should be this is a corollary of the fact that F is expanding. And probably their result could be generalized to more general hyperbolic dynamical systems. For instance, for all Smale spaces with one direction being a Cantor set. So not only for these Smale spaces, but say for Fibonacci tilings Smale spaces, things like that or Penrose tilings, that if you take the full group which I defined, then those full groups must be also F infinity. I don't know how to prove this, but morally that should be the reason. This hyperbolicity or the expansion property must be the reason why they are F infinity. Okay, so we got some finitely presented groups. So what? Maybe they all are the same, for example. Why this is interesting? Yeah, before I discuss that, let me give you some open questions. So first of all, it's not known whether contracting groups are amenable. It is known that they have no free subgroups, for example. But it is known that iterated monodromy group is amenable if F is a post-critically finite, in particular expanding on the Julia set, polynomial. That follows from a more general result of Bartholdi, Kamenovich, and me. It's not clear, it's not known when contracting group is, for instance, iterated monodromy group is finitely presented. Conjecturally, it happens only in virtually nilpotent case. So only in the case when M is a manifold. Intuitively, as I said, M is a manifold only in these virtually nilpotent cases. That's kind of follows from a theorem of Shubin-Gromov. So in all other cases, the space is fractal in some way. So it must be related perhaps to the fact that we get infinitely presented groups, but I'm not sure. Okay, so as I said, well, we get some finitely presented if infinity group, or even if infinity group. Why it is interesting? The fact is that this is a complete invariant, surprisingly. If you have two expanding maps, coverings, with path-connected spaces, then the associated groups are abstractly isomorphic if and only if the dynamical systems are topologically conjugate. So if and only if the dynamical systems are the same. So if there is a homomorphism of the spaces intertwining the dynamics. So it's a complete invariant. If you have two different dynamical systems, you know immediately that the groups are not isomorphic. So in particular, we get that there is only countably many expanding maps, such expanding maps. This is an old fact. This is well known for other reasons, like for the fact that they are finitely presented in the dynamical sense. So there is a Markov partition, and then if you know how tiles of the Markov partition are adjacent to each other and how they are mapped to each other, then you know the space. That's well known for people in dynamical systems. But here we get a link with group theory. And now a natural question is whether the isomorphism problem is solvable algorithmically. I don't know. It's an open question. So question whether if you have two expanding coverings, whether they will be given by finite amount of information, for example, by finite presentations of these groups. And you would like to decide whether the groups are isomorphic or equivalently whether the dynamical systems are topologically conjugate. And this is an open question. Nobody knows whether it's solvable or not. But this is some very particular class of finitely presented groups. Maybe it is possible to solve it. I don't know. So what is the scheme of the proof? So the first theorem is a black box by Matatyahu-Rubin, but also you can use results of, say, Hiroki Matsui, which immediately implies that, that if two such groups are isomorphic, then they act on the Cantor sets in the same way. So at least you can reconstruct the action on the Cantor set after topological conjugacy. That's not exactly what we need. We need M, which is a connected topological space. But one can show that actions of these groups on the boundary of the tree is an example of a hyperbolic groupoid. There is some generalization of hyperbolic groups to groupoids. In particular, you can look at the graph of the action, at the graphing. So you remember the definition of a graphing in Gabario's talk. He was working in the measurable category, and there one equivalence relation may have many different graphings. In the topological category, in the category of groupoids, graphings are like calligraphs. They are unique. They are up to quasi-isometry. So there will be only one quasi-isometry class of a graphing. And because the groupoid is hyperbolic, the components of this graphing will be Gromov hyperbolic graphs. And these graphs are, in fact, the Kelly graphs of the groupoid, in fact, are like orbits. So on a generic orbit, you'll get a Gromov hyperbolic graph. So you can look at the boundary. And the boundary of this graph will be a one-point compactification of some. So if you take one orbit, look at the graph, you take the boundary, it will be one-point compactification of a connected component of the natural extension. So natural extension is locally Cantor set times pieces of the space. Space is path connected, and the small space will be not path connected, but you can take the path connected components. So it will be some non-compact space, and when you compactify it, that will be the boundary. And it will be locally homomorphic to the space M, but it won't be quite the space M, so there is some more work to be done. But the theory of hyperbolic groupoids gives more than the space. It also gives something called dual groupoid. So on this groupoid, on this boundary, some other groupoid will act. And this dual groupoid will be Morita equivalent to the groupoid generated by the map. So you can reconstruct, at least up to Morita equivalence, you can reconstruct the dynamical system. Now you have to prove that Morita equivalence is actually possible only in the case of topological conjugacy. You do it by showing that, looking at path-connected components of the groupoid, you show that you can reconstruct the natural extension. And after that, it's not very hard to show that if two natural extensions are topologically conjugate, that the dynamical systems are topologically conjugate. So it goes through theory of hyperbolic groupoids and Morita equivalence and back to. So it's very topological. And if you are given two finitely presented groups in this class, I actually don't know any methods how you distinguish them, except for going through all this topology. Okay. So now I want, as a final example, I want to show you that these groups give a counterexample. I realized this just a couple of days ago only, and not during Hiroki Matsui's talk, but a couple of days after, that it gives a counterexample to one of his stronger versions of conjectures about relation between homology and abelianization. So as it happens, I know, at least for the case of complex rational functions, I know all these invariants. So suppose f is a post-critically finite hyperbolic complex rational function. So again, hyperbolic means that, well, for example, that if you take any critical point and look at its orbit, it's finite. So since it's finite, it will eventually belong to a cycle. And the requirement is that there is a critical point in that cycle. So in particular, if every critical point belongs to a cycle, then this is. So for z squared minus 1 is such an example. And let's take these three numbers. D is a degree. C is the number of attracting cycles, so the number of these cycles containing the critical point. And L is the GCD of the lengths of these cycles. So there are three numbers. That's enough. And there is one more condition. We say that a point is ramified, or is a critical value mod 2, if the difference of degree and the cardinality of the set of preimages is odd. So if it is not ramified at all, then this difference is 0. But if it is odd, that we say that it's ramified mod 2. Okay, so first of all, K-theory. So this GF is the groupoid of germs of the group VF, or equivalent to the groupoid of germs of the semigroup, which I will define by paths. So it's the groupoid acting on the Cantor set. So you can look at the C-star algebra of this groupoid, which is the same as reduced C-star algebra, because this groupoid will be amenable. It will be nuclear. The algebra will be nuclear. Then also there is, I wrote it this way, you can take the groupoid generated by the map F itself. So F is a local homomorphism acting on the Julia set. So it generates a tile groupoid of germs. So you just take the germs of this map F. On the Julia set, it will be some groupoid. So you take the convolution algebra of that groupoid. So in other words, basically, the algebra here is just, if you try to define what it means to be a cross-product algebra by the action of F, that will be that algebra. F is not invertible, but still you can define some kind of cross-product algebra. That's the cross-product algebra.
But there's a C star missing around out, right?
Yeah. So K0 is this number. So Z mod D minus 1Z plus Z to C minus 1. And K1 is Z mod LZ plus Z to C minus 1. It's interesting that these two algebras, the algebra of the groupoid acting on the Cantor set and the algebra of groupoid acting on the Julia set, belong to the class of algebras that are classified by their K-theory. They are whatever, nuclear, purely infinite, and so on. So this implies that these algebras are isomorphic. The algebra coming from the Cantor set and the algebra coming from the Julia set, they are isomorphic. But it's only through classification. You don't know any other. I don't know any other proof, and probably does not exist in a sense. Okay, so abelianization. If D is even, then abelianization of VF is precisely the K1 group, the same group as K1. If D is odd, and there exists an attracting cycle such that the number of ramified point, mod 2 points attracted to it is odd, then abelianization is the same. Otherwise, you get an additional Z mod 2Z. And conjecturally, but I am very sure that it is correct answer, the homology of the groupoid GF, of this groupoid acting on the Cantor set, is Z mod D minus 1Z in 0 degree, Z mod L, Z C minus 1 in first degree, and Z C minus 1 in second degree. But even if without this, it's clear that in this case, we get counterexample to the strong version of, how was it called? HA or AH conjecture of Hiroki Matsui. but not counterexample to the weaker version. So that's this Z mod 2Z. His strong version predicts that in both cases you get Z mod 2Z. But there are cases when this Z mod 2Z is killed. So that's the conjecture is that tabelization will be H0 modulo 2, so H0 modulo twice the group, plus H1. So H0 modulo twice H0 is trivial if D is even and Z mod 2 if D is odd. And this is H1. So that gives a counterexample. Okay, that's all for today.
Are there any questions? Yes?
Do you know anything about the day functions of these groups?
Sorry, den function? No idea. Do you know what's den function of Higman-Thompson? That's probably the first thing to understand is what is the den function of Higman-Thompson. Probably after that it should be easier. But I don't know what is den function of Higman-Thompson.
Yeah. In the classification theorem that you have, is it correct that any isomorphism between the groups is implemented by a conjugacy between them all?
Yes. I think, yeah.